Before we start, any questions about the course so far? No? Okay. So let me remind you just quickly what we did yesterday. So what we saw yesterday is that we started to study the constraints that conformal symmetry imposes on the actual observables of a conformal field theory, which are the correlation functions. And we focus for now on local operators. It should be said that conformal field theories have, apart from local operators, can also have operators that have extended object. You can have loops, for example. So far we're just studying the constraints that correlation functions are given on some endpoint functions of local operators. You can also study the constraints that conformal invariants, and I think this could be a good problem. You want to try? Of conformal field theory, you can define operators that are not supported at points, but supported on, say, a loop, a curve in space-time. And you can ask what are the constraints that, for example, a conformal symmetry would place on a correlation function on a loop operator that's supported, say, on a circle of radius r, and that's probed by a local operator at some arbitrary point x. So this is a loop, and this is a local operator. Okay. So you can try to figure out, using the same logic, the logic is always the same, what is the most general thing you can write on the right-hand side using the constraints of conformal symmetry. The fact that I use a circle is important because circles map into circles under conformal transformation. Okay, and then so we start with the local operators. And what we show is that they essentially fall into two classes. They're either primary, so these are the lowest weight states, and they're annihilated by the Specian conformal generator and transformed very nicely as tensors linearly under conformal transformation of the type infinitesimally parametrized by these conformal Killing vectors. Remember, the zeta mu is a conformal Killing vector that parametrizes which conformal transformation we're making. And what we saw is that, so this is a transformation. It has the obvious kinematical part that just translates the operator. It has a part that it's local rotation, local Lorentz transformation, and a local dilation with these parameters, okay? That depend on which transformation you made. Okay? In particular, yeah. And the quantum numbers that label the operator is this R, which is a representation of Lorentz, and delta, which is the scaling dimension. And then we could construct operators that you construct out of them, and they play an important role in the theory too. We will see this very clearly tomorrow, hopefully, which are called the descendant operators. And these are essentially just space-time derivatives of primary operators. These are operators that you get by acting with the momentum generator on a primary operator. Remember that the momentum generator raises the dimension of the operator. And so what you can do is you can act with the momentum generator in the conformal algebra, which is a raising operator on a primary, and it will increase the dimension. And it acts, usually the momentum generator, even in a Poincare invariant field theory, acts on an operator as a derivative. Okay? And this fit in a conformal family. That's what it means that they're in a representation of the conformal algebra. And to convince yourself that this is indeed representing the conformal algebra, what you need to check that if you make consecutive transformations, they close. Where this commutator is the Lie bracket of the conformal Killing vector fields that generate the conformal algebra. Okay? Good. So now that we understood how operators transform, we could go back to the thing that we care most about, which is to see the constraints that the extra symmetries that the theory has beyond Poincaré have on the correlation functions on the theory. So you want to see how the correlators are constrained by what are called the word identities. Word identity just means that is the constraints that follow from the symmetries of your theory. Okay? I'm just using that word in case you have seen it in quantum field theory, something or other. So we're just doing that. But except that we're now doing it for a more powerful symmetry, like conformal symmetry. Okay? So we want to see that correlation functions are what constraints conformal symmetry gives us. So for a finite conformal transformation like this, the statement that the correlation functions are conformally covariant is this statement, that the transformed operator evaluated at the transform point is the same as the original operator at the original point. Okay? At the same point. You have to compare them at the same point. Okay? The infinitesimal version of that is just that the variation of the endpoint function vanishes. Okay? Where the variation is exactly, we have to use this variation. Yes?
But you have to evaluate them at the same point? But like in a conformal field theory, for example, take the operator just being the field phi in a bosonic theory.
Yes.
But phi transforms, right?
Yes.
So phi tilde is just
these tildes have been the cause of infinite numbers of nightmares for many generations of students. So convince yourself that under a Poincaré transformation, this makes sense. Okay? No, they're not. I mean, in the sense that a scalar transforms. Say, take a scalar, for example. Transforms like that, right? Yes, that's what I mean, that's the scalar.
Yeah, sure.
But the infinitesimal version is just that the variation of the correlation function vanishes. And you have to remember that delta O1, O2 is delta O1, O2 plus O1 delta O2. Okay? Good. So given that we know explicitly what delta is, the variation is, this defines a certain system of differential equations that you can, I think you're going to be asked to solve explicitly today for the simplest case of 2- and 3-point functions of scalars. Okay. So what's the upshot of this? So the upshot of this, you can start systematically with starting with the lowest point function and constructing the, and increase the number of insertions. So we can start with the 1-point function. So the first statement is that the 1-point function will vanish unless the operator is the identity operator. And for this, it's sufficient to use a scale invariant. We don't need to use a special conformal invariant. For the 2-point function, we have OI, OJ. There are diagonal in their dimensions. So operate, okay, so the one thing that's very important, I'm talking about the correlation functions of primary operators right now. The correlation functions of the descendants are already fixed in terms of those, okay? So the correlation functions of, or the 2-point functions of primary operators are orthogonal, are block diagonal. You can only mix with operators of the same dimension. And then the 3-point function. So notice that now the only data that we can get from here essentially is delta I, which are the scaling dimension. Then we can look at the 3-point function. And this is really remarkable. that already the three-point function is still, the position dependence of the correlator is completely fixed. Ijk. So there is now a tensor, Tijk, right? That tells you how these three guys couple, and then everything else is completely fixed by conformal symmetry. So let me try to. Delta I plus delta J minus delta K over 2. Y minus Z square delta J plus delta K minus delta I, and X minus Z square delta I plus delta K minus delta J. Okay? So from these three-point functions, you extract an extra data that you have to understand. Ci, Jk, the tensor, is the coefficient of the three-point functions. Okay? So these are the basic data that we need to. So having a CFT essentially means, in particular, listing a set of delta S and a set of Cs. Now, another way to think about why the three-point function, the position dependence is completely fixed, is by noting that using conformal transformations, I can take arbitrary 3 points in space-time and map them to your favorite choice of 3 points in the world. So for example, 0, 1, and infinity. Can someone, okay, so let's do this exercise because I saw some faces that didn't believe me. So let's show that by sequentially using conformal transformations, I can map arbitrary 3 points, x1, x2, and x3, to your choice of reference points. Let me just choose 0, 1, infinity, say, okay? This is essentially the same statement as this. It tells you that the position dependence is completely arbitrary, and all that matters is the coefficient. So how will we try to do this? Yes?
There are 3 points, so that there's a plane that goes through all 3 of them. And in that plane, you can apply a Möbius transformation. I think
you skipped a million steps. I mean, ready to put them in the same plane, you have to do things, right? They're not, but in d dimensions. It's what you said is true, but after.
I have the wrong point on the unit sphere, and then I can just apply a rotation, and the problem is solved again.
Okay, so let me start more simply. Can someone tell me how because I think you essentially have done many steps, and I want to do it more slowly for if people are not familiar. So if I give you a point x3, imagine I want to put this guy at infinity. What would you do?
I do a translation to 0, then I can, oh wait. Can I use conformal transformation that are not connected to identity?
So try not to use that.
Okay.
But you were roughly in the right direction, so.
Right. Can you just put 1 to 0 first? Seems like an easier way to go now.
Actually, I think it's easier. I mean, I think it's more clear what to do. You want to get rid of the nastiest fellow from the beginning. So nastiest fellow is a special conformal, right? So by a special conformal transformation, you can map any point to infinity. And I mean, one simple way to understand it, I mean, you can just write. You can look at how special conformal transformations act, right? So. Oh, sorry. 1 plus 2b dot x plus b square x square, okay? But remember that this guy is I, b mu I. So all I have to do is I invert any arbitrary point. It lands me somewhere, then I translate to the origin, and then you kick me back at infinity, okay? Good. Then I can use translations to put x2 at the origin. And then, of course, x1 will go wherever it wants to go. And of course, the important point about translations is that they don't shift infinity, okay? But now I still have, so I have a point now at, I still call it x1, even though it transformed in some point, 0 and infinity. Now, what can I do?
I can rotate it and do a dilation and put it.
Yes, exactly. Yes. Okay, so maybe to be more explicit, you can choose a line from 0 to infinity and align x in that direction. So for example, you can take x to be canonically lambda 0, 0, if we're in the dimension, right? And then I can use a, so this is a rotation. And then I can use a dilatation to rescale this to 1. So in this way, we have mapped any 3 points to 3 reference points. Okay? So that just tells us that the position dependence is completely fixed. In an exercise today, you will see that here it is very important that we have special conformal generators. If we try to solve this problem only imposing, if we imposed only Poincaré plus dilatations, you would have here an arbitrary function that you have to determine. Okay? So in some sense, it's nature's gift that the theory is enhanced and a second order phase transition from Poincaré plus dilatations to special conformal transformations, because then you can measure, I mean, you can measure that this is what the correlations look like. I saw some hand, yes.
How is the angle preserved if they're all on one line?
Sorry?
How are angles preserved if they're all in one line?
I don't know what you mean by the angle.
Like, in the end, they're 0, 1, infinity, and they're all in one line. But initially, there were some arbitrary triangles. What the angle that we see could put in
Well, the angle
That's how
between,
you connect everything to infinity, right?
yes.
0, 1, and infinity can kind of make up an
Yes.
angle.
Yes. Okay, so now you could try to go on and say, you could wonder, can we continue forever and will everything be fixed? So the thing breaks down if I look at the 4-point function. So for simplicity, I'm now going to consider the 4. Oh, by the way, so far this is a discussion for scalar operators, right? There are no Lorentz indices. If there are Lorentz indices, it's a bit more tricky, but. So, and also just to make the discussion more simple, we're going to discuss 4-point functions of identical operators. Just so that there are less indices floating around, and just to explain what the basic idea is, adding more indices is completely trivial. So we're going to have OX1, OX2, OX3, OX4, okay? Okay. So something that, especially that happens when you have 4 points, is that you can construct certain coordinates that are conformally invariant. These are what are called the cross ratios. And we can define some, so this is something that one can check explicitly. Let me make sure that I use some reasonable convention. Oh my God, I'm going so slow. And the thing that's remarkable about these guys is that these are conformally invariant. So that means that since they are invariant under any conformal transformation, at the very least, I can write an arbitrary function here of u and b, because they're invariant, okay? Under any of the transformations. And this is something you can check. I mean, it's obviously invariant under everything except a special conformal, as usual. So it's obviously invariant under rotation, Poincaré and dilatations, but the special conformal you have to check. And so that's something if you're motivated, you can try to check. And then just by dimensional analysis, this guy I can write as x1t to the 2 delta, x34 to the 2 delta. Okay. One way to think more geometrically, so I'll just say the word now, and you can go ahead and think about it, because I don't want to take too much more time. One way to think about why there are two cross ratios for 4 points, is that we can continue this game one more step here. Imagine now I added an extra point, x4. I want to use a transformation that will not mess around with 0, 1, and infinity. Okay? So what I can do, let's call it x and y. I can perform a rotation around the one axis, okay, to bring the other point in a given plane, x, y. Okay? So that means that I can map x2 to a plane. So the 4 points are in a plane. And to specify x2, I just need two numbers, the coordinates in the x-axis and the y-axis. Okay? So we can use a nice complex coordinate. So we can denote complex coordinate z. So that means that there are two parameters. That means the correlation function depends on these two parameters. And now you can compute that this guy is z, z bar, and this guy is 1 minus z, 1 minus z bar. Okay? So just evaluate this cross ratio, which is valid at any point, on those 4 points. 0, 1 at infinity, and one of the points in with complex coordinate z, 0, 0, 0, 0. Okay. I'll come back to this tomorrow. So now here you would have thought, okay, this is bad. I have an arbitrary function that I know a priori nothing about. So it seems that you would have to use more data to specify a CFT than the dimensions and the structure constant. What we will show tomorrow is that, in fact, conformal symmetry, OP, so this is a word I'm not explaining now, I'll explain it tomorrow. What's called the operator product expansion in conformal field theory plus conformal symmetry allows us to write F UV that is determined by the let's use the word called CFT data. So we introduce now this notion of CFT data, which is going to be the collection of dimensions of your operators and your OPE coefficient. And in fact, this goes on even further. Any endpoint function is completely determined in terms of this data. Now you may wonder, is this data, can I have any data I want? I can give you an arbitrary list of numbers here. Will this be a consistent theory? And the answer will be no. This data has an important consistency condition that we will discuss tomorrow, if I ever get there. That puts very strong constraints or relations, an infinite number of relations that these numbers have to satisfy. And I will explain to you what this relation is. It's called a crossing relation. And how using this idea has recently led to a way of measuring without using perturbation theory, without nothing like that, just using pure thought in some sense. It has led to a way to measure the critical exponents extremely precisely of the three-dimensional Ising model, 3D Ising CFT. Okay? So this is very remarkable. Conformal field theories are essentially completely fixed by the knowledge of the 2 and the 3-point functions. Okay? This is definitely not the case in standard quantum field theories. Okay? And so tomorrow we'll continue with this discussion, and I'll write down explicitly more or less explicitly, the very nonlinear equations imposed on this data that the data has to obey. Okay? And in fact, I think next week, Dalimil, which is a graduate student, will give you one more lecture to go into the details of how this works. people have done, I mean, people have studied these equations numerically. In fact, he's one of the persons that has done it. So I will not explain anything numeric because that's not my expertise, but he will, I think. Maybe fill in some of the details that I will not have time to go into. But I certainly want to explain what's the basic idea, which is very simple, about DOP and how it constrains the CFT data. Okay, so now what I want to do is the following. So I already said that, that any CFT has the energy momentum tensor, right? So one of the things that we have to now worry about is what is the constraints on the correlation function of the energy momentum tensor. We want to know the 2, 3-point functions of the energy momentum tensor. So we could just use exactly the same word identities. We know how T mu transforms under a conformal transformation is a conformal primary. So we can just write down the differential equations. In order to motivate the answer, let's start with something that's a bit simpler. We can start with an operator that is present whenever a CFT has a global symmetry. So if a CFT has a global symmetry, you have a conserved current, okay? And by global symmetry, it means that it's not a space-time transformation. It's not part of the conformal group. It's like a flavor symmetry or something like that. Then we will start with something simpler, which is the 2-point function of the currents. And so this you can find in the notes, the details. I don't want to spend the time to go through the details. It's just rather elementary algebra. But this allows me to introduce a tensor that plays an absolutely fundamental role when you try to constrain the correlation functions of operators that carry a spin, because now this guy has spin. It's a vector. So there is a certain tensor, I mu nu xy, that is the solution of the conformal word identity. So just like in the 2-point function, 1 over x minus y to the 2 delta was the solution for the 2-point function of a scalar. For a vector, you have to introduce this gadget this tensor I mu nu, okay? So now let me make a couple of comments. So what is this I mu nu? So I mu nu is a very nice tensor. I mu nu is related to the Jacobian produced by inversion. Remember that under an inversion, x mu goes to x mu over x squared. So let's call it, let me say it like this. Then the Jacobian, that's what it means, the Jacobian of the transformation, right? This defines a matrix. And should be clear that that's that, okay? And this guy is precisely this tensor I mu nu of x, okay? And the thing that you can check is that this guy is orthogonal. So I transpose eta I equals eta. So it's an orthogonal transformation. And this guy has, the reason that this guy enters in all these equations when you look at correlators of operators with spin is that it satisfies the following relation under a conformal transformation. So sorry, hope I don't make a mess, but I think this is true. Rho sigma of x minus y, O sigma nu of y. So imagine that so exercise, check that under an inversion, the I tensor transforms like that. This is something that you should more or less recognize. This tells you that this guy transforms as a connection. Because I have 2 points, I do a transformation and I act with a matrix on this point and on this point, or on the other point. This is just like if you've seen in gauge theory Wilson loops. You have the holonomy of the Wilson loop. If you make a gauge transformation, it's acted on the right and the left at the endpoints of the Wilson. So by solving the conformal word identity in finite form, so something like G mu x tilde G nu y tilde equals G mu x tilde G nu y tilde, and using the fact that you know how J transforms, the conformal primary of dimension delta, after 3 lines, you should be able to, okay, once you're kind of given this hint that there is this guy that has this property, you should be able to derive that this is the form of the 2-point function. Okay. Now, notice that here I have only imposed conformal symmetry. Now, which property? Okay, so it is not guaranteed that if I act here with a derivative, that this will vanish, right? Even though for a conserved current, this should vanish, right? Because d mu, j mu vanish. So can someone guess? So and generically, it will not vanish. If I act d mu on this guy, it will not vanish, except if what is the dimension of delta? Except if I tune the dimension delta. So can someone tell me what, just intuitively, what dimension delta will have the property that the correlator will be automatically conserved? This may not be totally obvious, but you think about it for a second. Anyone wants to make a guess? A hint is that you know what the dimension of the energy momentum tensor is. And we know that all the conformal generators are written in terms of the energy momentum tensor. And that to construct the chart associated to a symmetry, you have to integrate over space. Okay, so essentially the dimension has to be d minus 1, okay? Because then the chart associated to this current, which is a commute with a conformal group, will be dimensionless. Because I'm integrating J0 over dd. Okay, so the charts associated to the conserved current is integrating over fixed time slice, right, of J0. So this tells us that Q will have dimension 0. And in that, indeed, I mean, the dilatation operator will commute with this guy because it has dimension 0. Because it's a global symmetry. It means that it has to commute with the full conformal group, conformal algebra. Good. And now let's go back to the guy that we really care about, which is the energy momentum tensor 2-point function. And I'll just write down the answer. Essentially, it's all fixed by symmetry. And the building block is precisely this inversion tensor. I call this I call the inversion tensor. So let's look at kind of, if you wish, one of the most basic things that we would care about in a conformal field theory, which is the 2-point function of the energy momentum tensor. So this guy will have to go like 1 over x minus y to the 2d. That's just a statement that the energy momentum tensor has dimension d. And now all I have to do is write down something that will have the symmetries of this gadget. It has to be symmetric and mu nu, and yes.
Can you repeat the argument from there? I have no clue what you just said.
The argument is that imagine J0 had dimension scaling dimension different than d-1. Okay? Then Q would have dimension non-zero.
Yes.
So then it would not commute with the dilatation operator, which measures the dimension of the object. And a global symmetry commutes with the space-time transformations. Like a flavor symmetry commutes with the space-time
You're
transformation.
saying that J should always have that dimension.
Yes, they're important. Any global symmetry, the current has to have dimension d-1. This is a universal result. Yes. So now I can use my IMU business to write something that's essentially completely fixed. Okay, so I define, maybe let me do it into, so I define this tensor I mu nu rho sigma, which is a function, of course, of x minus y by translational invariance. And this, I can write it just, is 1/2 I mu rho x I nu sigma plus. I'm just symmetrizing. I'm doing just making sure that the Lorentz indices on the left and on the right make sense. Okay. So this tensor is the unique symmetric traceless tensor that you can write down.
I still don't understand why Q has to commute with the conformal algebra.
No, because this is the definition of a global symmetry. A global symmetry, which is not by global symmetry, which is not a space-time symmetry, is a generator that commutes with the space-time symmetry.
Wait, what? Global symmetry? That's not a space-time symmetry?
Yes, because I want to distinguish the space-time symmetries, like conformal symmetries, from things like flavor symmetry.
So when you say a global symmetry, that implies that it's not a space-time
Yes,
symmetry?
definitely, yes. Because that's the standard nomenclature. I mean, look at the energy momentum tensor, right? The energy momentum tensor is a space-time current. It has dimension d, not d-1. So the space-time symmetries are really different than the other one. Okay, and this defines, okay, so this introduces this quantity C. So there is a constant here that sits in front of the correlator that now we want to discuss a little bit the physics of, okay? And this guy plays an important role in many respects. And it's, I mean, especially in two dimensions, so two space-time dimensions, so d equals 2. C captures lots of physical properties of your conformal field theory. Okay? And what I want to describe now is that this C can be either measured by the separated point, two-point function of the energy momentum tensor, or by coupling your CFT to a background metric. And then C there, okay, so then C. So C can be measured from a flat space correlator, or by coupling from flat space to curved space, okay? And then this guy, C, in that case, C gets an interpretation. C is interpreted as a conformal anomaly. Okay? Which I will explain what this means. It is the statement that the trace of the energy momentum tensor in flat space in a conformal field theory has to vanish. That's something that we established very early on, right? Okay? And C will be a quantity that if I put the theory in a curved background, we will find that T mu mu is different from 0 and proportional to C. Okay? So it measures the violation of the tracelessness of the energy momentum tensor, and namely it is a violation of the dilatation symmetry. Remember that P mu mu was essentially the P mu mu. It was the derivative of the dilatation current. Okay? So it's a violation of the dilatation symmetry once you couple the theory to background metric. So, but we're going to discover this anomaly, if you will. This guy is called an anomaly, and I believe in the third week you're going to hear more about anomalies. He'll give a very down-to-earth point of view where you discover the anomaly by just studying the theory in flat space. Okay? You will see that consistency conditions will lead us unambiguously to the fact that this guy has a non-zero right-hand side once we couple it to the background metric. So what I want to study now is the following exercise. Actually, it's very similar to this exercise, but I'll do it in momentum space because it will be easier to read the anomaly. So let's look at the two-point function of the energy momentum tensor in momentum space. And here I'm using momentum conservation, okay? So in this lecture, in this afternoon's tutorials, what you're asked to do is to write down the most general expression consistent with Lorentz invariant and Bose symmetry, which means that whatever you write here should be symmetric under the exchange of mu nu and rho sigma, okay?
Well, one question, why, sorry, are we putting P minus P?
Okay, because this essentially follows from translational invariant.
Okay.
If you want to be more precise, but then I have to write more, you would write here Q,
Okay.
and then here you would have a delta of P plus Q. Actually, keep this delta in mind because when I do dimensional analysis, I will have to use it.
Okay.
But I'm just solving for the delta function. Okay. And what you should find is that actually there are 5 different structures that can appear here. And all that you have to write them is the basic kinematics of the problem. You have the metric, and you have the momenta, P mu. Okay? And now you have to write down all possible combinations of P and eta that obey this property. Okay? Okay, now we impose the fact that the energy momentum is conserved. I have not imposed conservation here at all, right? Just Lorentz symmetry. So now what I do is I impose conservation. So in momentum space just means that I can act, say, with P mu. Okay? And impose that the energy momentum is conserved. Okay? This will give relations between the various coefficients that appear here, and you end up with 2 independent structures, which have a clear physical meaning. So let me. By the way, this is an statement that so far we're in arbitrary dimensions, D. Okay? Have T mu nu P, T rho sigma minus P. So let me introduce this notation that you may have seen before in quantum field theory. So let's make sure I don't mess up the indices. Mu rho mu sigma plus mu sigma mu rho minus 2 over d minus 1 P mu nu P rho sigma, and an arbitrary function of P squared. P squared is a Lorentz invariant, so I can have a function there. And I get then a second term, which is P mu nu P rho sigma G of P squared. Okay? So this is the most general form of a 2-point function that is conserved in a Lorentz invariant theory. This guy can be thought of as symmetric traceless and this guy is the trace. It has an uncertainty. Okay, but I didn't tell you what P mu nu is. So P mu nu is essentially P mu, P nu, P square eta mu nu. Why is it nice to combine the momenta in this way? Because this guy has which obvious property? Yeah, so it's automatically conserved. Okay, so you write something, we're imposing conservation, so everything on the right-hand side is manifestly conserved under all indices. Okay, so that's a good thing to do. Now, to introduce to this subject of anomalies and their importance, let me just, let's restrict our attention to 2 dimensions. So in 2 dimensions, something very special happened. This guy, in 2 dimensions, the first term just vanishes. Okay, so in 2 dimensions, all that we have is this. So T mu nu, P rho sigma equals that guy. So pi mu nu, pi rho sigma as a function, and a function of P squared. And this essentially just follows from the fact that you can decompose, okay, so that in 2 dimensions, the kinematics is very special. I can define a tensor P tilde mu nu, which is something like epsilon mu lambda P lambda, okay? And then, given this definition, you can see that P mu nu is proportional to the product of these P tildes, okay? So now if you look at here, you will see that in D equals 2, these guys, all the terms are the same. Because you have this is just the product of all the 4 P's, right? Of all the 4 P tildes, right? You have 1 plus 1 is 2, minus 2 is 0. So you only are left with this gadget, okay? Is this clear? So which part do you want me to? So these follow, okay, so this, if you want I can write this follows from this, just from the fact that I can decompose in 2 dimensions the product of Levi-Civita tensor okay. So this implies this, okay? So that means that, what is this then? This is just the product of P mu tilde, P rho tilde, P nu tilde, P sigma tilde, right? But this is exactly the same, because all indices appear in each term.
How did you go from the right to the left?
How did I get from where?
How did you see that it is proportional?
Well, you use this identity. You use this identity, and you use the fact that P mu nu is this. This is not deep. I mean, this is really not deep. Just
maybe it's not deep, but it's also not 1 second.
No. So I'm not saying, yeah. So this is something you can. It will take you a minute and a half to you sit down and do it. If you multiply these 2 guys, you're going to get precisely these 2 structures.
Okay.
I mean, try it for 2 minutes and you will get it. Yeah. Okay. So summary. In 2 dimensions. In 2 dimensions, we have that I can write it now. So P mu tilde, P nu tilde, P rho tilde, P sigma tilde, and then some arbitrary function of P squared. Okay? Now I'm going to use that the theory has conformal symmetry. So that fixes the momentum dependence of this arbitrary function, because we have to use dimensional analysis. The dimension of the left-hand side has to be the same as the dimension of the right-hand side. The Fourier transform of the energy momentum tensor has dimension 0, because I'm integrating over space. So I have dimension 0 here. Here has dimension 4. And remember that here, there was this funny delta that I had dropped, but we have to remember that it's there. So this, okay, so this has dimension 0. This has dimension 4. Here I have dimension -2, plus I have the dimension of f, okay? So this tells you that f has dimension -2, okay? This tells immediately that f has to be a constant divided by p squared, okay? So this fixes completely the dependence of the function on p. So I'll do something that's not legal, but I'll do it anyway. So I'll just erase and put here t, 1 over p squared. And notice that we get here this number c, which is not a coincidence. It will be, of course, the same number as before.
How do you see that it's the same number?
Well, because, okay, so one way you would see it, just at separated points, just do the Fourier transform of this. If you do the Fourier transform of this gadget, you're going to get that in position space. I mean, you can compute the 2-point function of a correlator in position space or momentum space. They're related by a Fourier transform. Now we will see that something very funny is happening. So this correlator has the property that it's conserved by construction, because again, p mu, p tilde mu is 0. Because you have an epsilon tensor that multiplies, which is antisymmetric, multiplying two momenta, which are symmetric, so that gives you 0. But now we see that there is a fundamental problem. We started with a theory that, well, it's not a problem. It has the following feature. Now we can try to see what happens if I take the trace of the energy momentum tensor. So imagine I take the trace, say, of this guy. So I compute p mu mu at p, p rho sigma minus p. So all I did is I contracted this equation with eta mu nu, okay? So all I have to do is I have to contract p nu tilde with eta mu nu. And again, this guy just gives you p squared. Okay? Notice that this p squared will cancel precisely the 1 over p squared here. So I'll get c, p rho tilde, p sigma tilde. Okay? So this leads to something you could call a puzzle, because I have told you before that CFTs have a traceless energy momentum tensor, but now I found a correlation function in which p mu mu is not 0. But actually, it is 0. Okay, so it is 0 at separated points. So let me try to explain. I mean, this is a simple point about Fourier analysis. The thing that's special about the right-hand side, as opposed to this object, is that this guy is a polynomial in momentum, okay? While this guy is not polynomial, it has a 1 over p squared. If I Fourier transform 1 over p squared, you get something that has support at separated points, okay? Like if you do the Fourier transform 1 over p squared in 4 dimensions, you get 1 over x squared. Yeah. While, what is the property of the Fourier transforms of polynomials of momenta? What do you get? Just try.
Yeah, I mean, I would associate it to derivatives of the phi.
Derivatives of?
Derivatives of what I'm transforming, but let me think a little.
Yeah, it must be perfectly local, because that's perfectly smooth.
It's going to be ultra local. I'm already giving you the, it's not local, it's ultra local.
But this ultra local.
Once you know the answer, you will understand why I say ultra local.
It's in a point.
Yeah, it only has support at a point.
Yeah.
I mean, the Fourier transform of 1,
It's called quasi-local.
the Fourier transform of 1 is a delta function
Yes.
With the Fourier transform
of 1.
Yeah.
Is a,
very hard to Fourier transform.
is it, no, you get a delta function. Dirac delta function. So the Fourier transform of polynomial is a derivative of the delta function. So, okay, so if I Fourier transform now, I expand this guy, so it's something that you will recognize more. D rho, d sigma. We'll have a C minus box. That's just, okay, that's just delta square. Eta rho sigma, acting on the Dirac delta function. So this is a statement that the energy momentum tensor is traceless except at coincident points when this guy hits here. Okay? But usually when we study correlation functions in flat space, we always study correlation functions at separated points. The physics of conformal field theory, I mean, axiomatically define it by studying the correlation functions at separated points. So this doesn't give us trouble, except if you couple the theory to curve space. So let me just quickly tell you what happened. So now let's see that this leads to a conformal anomaly. Now let's imagine that I want to compute d mu mu at the origin once I couple, I'm in flat space, but now I couple it weakly to a curved background metric. So I couple it to a metric. This to leading order in the coupling of the metric can be thought of as this. Right? The coupling of a theory to a metric perturbation is through the energy momentum tensor. So in the language of Lagrangians, what you do is you add to your Lagrangian the coupling of the metric to the energy momentum tensor. Okay? And now let's compute this for a small h to leading order in H. So the leading term will be just the 1-point function. And then, of course, I evaluate at the end in flat space. Okay? I do a perturbation theory in H. The 1-point function, I already said, that vanishes for any operator other than the identity. So the first term arises from the 2-point function. So I have the integral of dx, d mu mu 0, t rho sigma x, h rho sigma x. Okay?
If you add something in your action and then you calculate the correlation function, then like you're thinking of path integral formalism, right?
I don't need to think about it. You can, there's an object in an abstract conformal field theory that is the generating function of all correlation functions, where you add a source for all your operators, and you get a correlator by doing the functional derivative with respect to the source. But we can talk about Lagrangians if you like. I mean, I'm not.
I mean, if like okay, if you think about path integral formalism, don't you need that extra exponential both in your numerator and in your denominator? I'm very confused. Like, if you calculate an operator given a certain action, then
yes.
You're like calculating the path integral of that operator times e to the power of that action divided by the path integral of that action.
Yes, but this will be.
But here, there's no, that part of your action is not there in your denominator.
I'm not normalizing things yet. Can I finish? We can go back to what you were saying. I know what you're saying is not really relevant. Not really relevant. Do you agree that if you define your action, you have to add this operator?
You have to add that to your action, sure.
Yeah, so that's all I did. That's all I did. And now I'm expanding in that.
I don't see how that's all you did. That's my question.
Okay, since I don't really understand the question and there is not much time, can you ask me after the class? Yeah. I mean, this is how you couple current, the conserved current, to the corresponding gauge field. That's all I'm doing. In this case, the current couples to the metric. If it was another current, would be A mu, J mu. And I'm expanding in a small a. The leading term, as I said, is the two-point function. And now we can use this, what we derived here, and integrate by parts. So I can take this guy and hit it on the metric. And integrate the delta function to get this. So d rho, d sigma minus box eta rho sigma acting on h rho sigma of x. Okay. So now what I see is that p mu mu, this is an operator equation. This is an equation that's true inside your path integral. That's what operator equations are. Okay? So what you find is that this is, now it's not, p mu mu is not a contact term. It has finite support, right? Non-zero everywhere. So it means that if you couple your theory to a background metric, the energy momentum tensor is no longer traceless. Now, of course, the theory is still covariant because I impose energy momentum conservation, right? So what is this object? I mean, do you recognize something that's covariant, that two leading order around flat space look like this?
Christopher?
Sorry?
Not like the connection?
It's the Ricci scalar. So this is C, R. If you look at the Ricci scalar and you expand it around flat space, and you expand to leading order in H, you get precisely that. Okay? So this is the statement of the conformal anomaly. So I just derived it from a very down-to-earth point of view where you study in flat space. There is there's a different way of doing it, which you study the theory directly in curved space and use certain consistency conditions that determine all anomalies. And then if you do it so you could try to now do it to higher orders in A. And what you would do by covariance, essentially, you would build up exactly the Ricci scalar. Okay. So this is to say that this C has this other physical meaning, which is a conformal anomaly. Okay? And the reason that this is important, I went through this, is that conformal anomalies in 2D and 4D. Earlier in the lectures, I said that you can associate a quantity between two RG flows. To start with a CFT in the UV, you perturb it by a relevant operator. You end up with a CFT in the infrared. We could associate a quantity that is monotonic in the flow, so that the C of the infrared CFT was always smaller than the CFT in the ultraviolet. And the point is that these C's are precisely these conformal anomalies. So these violations of the energy momentum tensor to when you couple it to curved background. More generally, if you want to do it in odd dimensions, you may or may not know this, and if you're interested, I can explain why the next time there is more time. There are no conformal anomalies in odd dimensions. Simply because, essentially, there is nothing you can write down on the right-hand side that makes sense dimensionally. P mu mu in 3 dimensions has dimension 3, right? You have to write something on the right-hand side that would be generally covariant and has dimension 3. There is simply no such thing, because essentially all the Riemann curvatures have dimension 2. So, but there is a quantity in all dimensions that has this property. Let's call it C, even though different dimensions have different names, but let's call it C for completeness. But there is a way, the reason I went to this curved background business is that there is a universal way of characterizing what is the quantity that has this monotonic property in any dimension. And this quantity is measured by studying the partition function of your conformal field theory, not in flat space, but on a round d-dimensional sphere. Measures the monotonic quantity. So in even dimensions, this guy picks out precisely this conformal anomaly. In 2 dimensions or in 4 dimensions, there is an analog of that that's proportional to the Euler density. While in odd dimensions, this quantity is well defined and defines an observable that has these monotonic properties under RG flow. And this kind of global way of thinking about RG flows and the importance of defining theories on a sphere, on a curve space, which is not something that you would want to do because we don't care about we don't really care about curve space. We care about flat space. But the beautiful thing about this is that by studying the conformal field theory on the sphere, you're measuring an observable that you care in flat space. It's a way of extracting an observable of the theory in flat space by changing your geometry. Yeah. OK, so unless there are questions, and you can ask me maybe now, we'll continue tomorrow.